Hello, welcome to the Engineering Mechanics Tutor in Statics. We're going to have a batch of lessons here that really builds on everything we've learned so far in engineering mechanics and extends your knowledge, and everything will be taught with step-by-step example problems. So what we're going to do in this lesson is begin the process by talking about the moment of a force, the scalar calculation of a moment of a force, and this will be part one. We'll have several lessons that follow that will get into more or different cases and a lot of example problems so we can get you some practice. Basically, we have the concept of a moment of a force that we're going to talk about right now, and in this lesson we're going to focus on the scalar calculation of that. What I mean by that is really the moment of a force is really a vector, and when we really calculate it in its full glory, eventually we're going to use the cross product of two vectors, which we haven't even discussed yet, to calculate the moment of a force. But before we get into all the cross product business and dealing with all that vector stuff, it's really easy to understand the concept of the moment if we simplify the problem and look at a scalar calculation of it. In other words, don't worry too much about its vector nature yet. Don't worry about the cross product. Just we'll take some simplified problems in 2 dimensions, and you can actually solve quite a few problems by doing it that way to begin with. So what we'll do over the next 3 or 4 sections is we'll talk about scalar calculation. We don't have to worry about I, J, and K in terms of the vectors. And then eventually we'll talk about the cross product, and we'll teach you how to calculate the moment in 3 dimensions when you really have to deal with the vector nature of what we're talking about. So the first thing is, what is the moment of a force? If I had to draw a definition or write a definition on the board, the moment of a force, or a moment, is basically, I'm going to put in quotations, the turning force about an axis. So if I wanted to write a definition, the moment, all right, is basically, I'm going to put it in quotes because you're probably not going to see this definition in a book, but it's kind of my definition. I'm going to call it the turning force about an axis. What do we mean by that? What we mean is regular forces, they act in a line, right? So if I have this pin here and I push on it, it's going to move in a straight line, okay? But we all know that we can rotate things. And if you think about it, when you rotate something like a faucet or a valve or something, what you're doing is you're grabbing the edges of it and you're applying a force tangent to the edge of the guy. So if you were to zoom in and look at your hand, you're applying a force kind of tangent, just touching the edges, and that's imparting a tendency or a moment for that guy to rotate about an axis. When we talk about moments, it doesn't make any sense to talk about a moment unless you're talking about an axis or a point about which something is rotating, because moments always deal with rotations. So far we've always been talking about linear forces pushing in different directions, and now we introduce the concept of the rotation or the turning moments of something. So as we eventually, the big pictures, we'll get to talk about equilibrium when we have to talk about rotational effects, rotational equilibrium, in addition to the other equilibrium we've talked about with forces. So this is the other big piece. Kind of everything we've been doing so far with forces is the peanut butter. The moment here is really the jelly. You put peanut butter and jelly together and you can solve a lot of different kinds of problems in the real world. So we said it was a turning force. I put it in quotations because it's kind of a nice, easy thing to understand. But really a picture is better than any of that stuff. Pretend for a second that we have some kind of nut, right? Like a hex 6-sided nut, right? And I've screwed it into the board, right? And I would like to unscrew it. Well, what I need to do is hook some kind of a wrench onto this, and I'm not a very good artist, so just forgive me here, but this is my concept of a wrench. It goes out like this, okay? Some kind of a wrench, some kind of a device that you basically attach to it, and it allows you to grab it so that you can move this thing up and down. Now, of course, I haven't drawn my wrench perfect. It looks a little bit like a whale. Okay, it looks a little bit weird. But the point is that there is some axis of rotation. Where do you think this axis is going to be in this case? Well, basically, I'm rotating about some axis O. And a lot of times in your problems, the axis of rotation will be denoted O. Could be anything you want. You could label it alpha, beta, gamma. You can label it anything you want. Typically, we're going to use O to denote the axis of rotation. Now, you know that if you grab this thing and push it up like this, it's going to begin to rotate in a circle such like this. So to make this clear, we're going to actually grab it and we're going to push straight up. We're not going to push at any angle or anything. We'll get to talking about what happens when you put an angle on your force later, but for now we're going to rotate, we're going to push up with a force. And this force, as we do that, is going to cause this guy to rotate. So what we say happens, all over to the side here, this is going to cause a rotation that's going to go like this. So I have like a little arrow going like that, indicating the direction of the rotation. The other thing I want to point out here is that basically we have two important lines here. We have the line of action is what we call this guy. The force acts along this green line, okay? Forces always have to act in some line. Now, yes, of course the thing's going to rotate a little bit. So just a few seconds from now, it'll be up here, but then the force will have rotated. If we continue to keep my force perpendicular to the wrench, as it rotates, the force will move more and more slanted, but at any snapshot in time, the force will act along a linear line of action. So this is called a line of action. It's important for you to know the terminology because when you're reading in your book, or if I'm explaining something to you, I might say, hey, this force is acting, look along this line of action for some calculation, and you need to know what that means. A line of action just means draw a line through the force, and the force is basically acting somewhere along that line. Now, I don't want to clutter this drawing up, but there's another line that's important here that extends from the axis all the way out to the line of action. Notice that this line and this line, I've drawn them perfectly so they're 90 degrees. Everything's perpendicular, which would be how you would attempt to loosen this guy. You wouldn't try to push like this. You wouldn't try to push like that. You're going to try to do this. It turns out that when these two lines, this line here and this line here, are perpendicular, you get the maximum moment, which is why when you use a wrench, you always do it that way. You always naturally push perpendicular because you get the maximum turning force, which is what we're calling a moment. All right? Now, one important thing I want to show you is that we have to have a sign convention when it comes to moments. Just like when we did static equilibrium of particles before, we said, hey, if your force acts in the positive x-axis, put a plus sign on it. If your force acts in the negative x direction, we'll put a negative sign on it. Same thing for the other directions. We have to have a sign convention for moments as well because we can obviously turn this thing this way, or if we reverse the force down, we can be turning it the other way. So we have to have a way to keep that in line. So the way you do that, or to keep it separated, if you turn something counterclockwise, which means the rotation looks like this, okay, that means that the moment is positive. Okay, so it's a positive moment. So in your equations, if you're figuring out something is turning counterclockwise, you put a positive sign on its moment. If you find that something is rotating clockwise, which is exactly the way a clock rotates like this, then you put a negative moment onto that guy. Okay, so this you may confound you a little bit at first until you realize that from trigonometry, remember from trigonometry we have an XY plane and we talk about measuring angles. We always measure angles from the horizontal, we measure them like this, and those are positive angles. And then we also measure negative angles below the axis like this. So it's exactly consistent with this. As we move counterclockwise like this, the same way that we would measure an angle, we use a positive moment. If we measure this way, which is clockwise, it's a negative moment. So if you get confused about which way it is, just think about the way you measure angles in trigonometry. All right, so we've talked about this magical force, magical turning force, that is basically acting on this axis of rotation. We know it's called a moment. How do we calculate it? Well, keep in mind I have a simplified case here. I have a force that's acting directly on a line and perpendicular to this line. So in this particular case, the way I've drawn it is basically just like this. And the angle here is 90 degrees. So if you have a case where the line of action and the line intersecting your axis is 90 degrees, then the moment is very easy to calculate, and it's as follows. The moment about axis O, there's a reason we have an O here, is we have to specify what axis we're talking about, or what point. Is very simple. It's just the magnitude of this force times d, where d is the distance from the axis to my line of action. Okay? So again, we talk about the moment about an axis, and this is called the scalar calculation. The reason I'm calling it scalar is because really the moment is a vector, and I'll explain why, and I'll tell you a little bit more about that in just a minute. But to get the magnitude of the turning force of the moment, all you do is you simply multiply the force times what we call the moment arm. So here we define a few other terms. This distance d, okay, I'll come over here and call this the moment arm. Typically you'll see that. And this F, we call it that F acts along the line of action. Right? So it's everything that we have drawn up here, just in words, we're expressing this guy. And when you multiply these two guys together, what do you get? You get the moment about point O. And by the way, when I say the moment about point O, what I'm really saying is there's an axis going through the board. Think of like a bicycle wheel turning around an axis. And when I say about point O, what I'm really saying is the moment about the axis that passes through point O. That's really what I'm saying. But since I have a two-dimensional drawing, we can just say for now that the moment is there. Now, I think I've been pretty clear about everything so far, but I want to point out something that's absolutely fundamentally so incredibly important, so I'm going to emphasize it a lot. It's something that you probably already know, but I'm going to emphasize it for you anyway. In this calculation, when we're finding out the moment about point 0 or point O with force F and moment arm D, okay? The only thing that matters in this calculation is the perpendicular distance, or I should say the force that acts perpendicular to this moment arm. Now in this case, the force as I've drawn it is already perpendicular to the moment arm. That's why it's F times D, okay? But as we get into more and more problems, I'll have different configurations, and you need to train yourself that the only thing that matters is the component of the force on that line of action that's perpendicular to the moment arm. Later on down the road, I'm going to show you what do you do whenever this force is cocked off at an angle, and I'll give you a preview. When you calculate the moment, you don't care about how much of the force is acting this way. All you're going to care about is the component of the force that's acting perpendicular to this moment arm D. So keep that in mind. I'm not going to write that down, but I'm going to say it over and over and over again. All that matters here is the force that's perpendicular to the moment arm D. Okay, now let's spend a few minutes talking about the direction of the moment. Now, I kind of hinted before a few times, and I actually told you that the moment is actually a vector quantity. In reality, if you have an arbitrary, moment arm and an arbitrary force, really what you do is you do the cross product of the two vectors. We're going to get to that later. What we're doing now is we're looking at everything in two dimensions because it's much easier to get a lot of ingenuity and or a lot of insight, a lot of practice when you do those problems like that. But I've already hinted that even though we're doing a scalar calculation, these are just two numbers we're multiplying together in this case, that there is a direction associated with that, and so I'm going to talk about that direction now. Whenever you multiply a force times a moment arm, and remember, only counts as the force that's perpendicular to the moment arm, then there's a couple of really important things that pop out of that. The direction of the moment is along the moment axis. Whoops. The moment axis. So I'll just kind of cut to the chase, even though we're not talking too much about vectors. The moment of a force is a vector quantity. That means the moment has a magnitude, and that's what we've really calculated here, the magnitude of the moment, and also has a direction. The direction is a vector that points along the axis of rotation, basically. When you think about it, if you're going to write a bunch of equations that involve moments and things that are turning, how are you going to really represent which direction everything's turning? Are you going to draw a bunch of arrows that are like counterclockwise and clockwise? I mean, you could do that, but that's very cumbersome. Besides, what mathematical construct are we going to use to represent like a counterclockwise rotation? There's not anything that's very easy to think of that can do that. But what we end up using is the concept of a vector. Basically, in this particular drawing, the moment, which is a vector, passes through this axis, and it's actually pointing out of the board. The length of that vector is going to correspond to the magnitude or the strength of that turning force of that moment. The longer the vector, the stronger the turning force, stronger the moment, okay? The direction it's pointing is coming, in this case, out of the board. So when I say the direction of the moment is along the moment axis. It's a little bit silly. What I'm trying to say is the axis of rotation passes through this point. The vector lies along that axis. And more specifically, the direction of the moment, here I'll put a little vector symbol over there. The direction of the moment is always perpendicular to the plane of F and D. Now, that might blow your mind a little bit, because you probably haven't thought about it too much, but what I'm trying to say is, when you think about it, the reason we start talking about things in 2 dimensions is because they're easier to understand. Here is a force, here is a moment arm. Basically, they form 2 lines, and so these 2 vectors, they form a plane. And whenever you think about it, any 2 vectors, even in 3-dimensional space, if I have one here and one here, they're always kind of form their own plane. So here's a vector, they form a plane. Here's a vector, they form a plane here. Every 2 vectors that you pick can always form their own plane, okay? And what I'm saying is, because the force is acting, on that moment arm and causing a rotation, and the axis of rotation is always going to be passing through that point there, and because the direction of the moment is always along the moment axis, then that means that the direction of the moment is always perpendicular to the plane that contains the two guys to begin with. So in this case, the plane is the board, because we have F and D, so we have a plane that contains these 2 guys. The moment axis is always perpendicular to the plane of F and D, your force and your moment arm. Always, 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 always. Doesn't matter if it's 3-dimensional, 2-dimensional, whatever. The moment's always perpendicular to those 2 guys because of the way we've defined it. Okay, and then finally the punchline here, the thing I really want you to remember, the direction of the moment is basically governed by something we call the right-hand rule. Okay, so I've kind of hinted about what the direction of this moment really is, but basically what it is, I could write it all down, but essentially the right-hand rule is you look at your right hand, and you look at this and you say, okay, if this force is acting up and this moment arm is here, how should it turn? Okay, and I've already told you the moment being positive or negative based on that rotation, but that's just the plus or minus of the scalar version of it. But for the full vector version of it, what you do is you take your fingers and you curl them in the direction of rotation. So in this case, here's F. So I'm curling my fingers as if this thing is rotating like this. And what's happening is my thumb is pointing out of the board. So that means that the moment vector is going to come through this axis and point out of the board. Okay? So if I'm looking down, for instance, we'll just draw a little picture of this. If I'm looking down, okay, so basically we're going to look down as if we're doing something like this, then there's basically 2 possible situations. Here is your point O, okay, here is your moment arm D, and here is your force. Let me switch colors here. Here is your force F. Okay, what do you think is going to happen in this particular case? Here is F, and here is D. So if I have, like a piece of wood or something sticking out from some axis or some point of rotation, and I push it like that, how is this thing going to rotate? Well, I take my hands and I curl them in the direction of the force, so that means that my thumb is coming out of the board, and that basically what that's telling me is that this guy is going to end up rotating like this, okay? It's going to end up rotating like this, and because it's rotating counterclockwise, the moment is positive, okay, and the moment is coming out of the page, which is positive z-axis. So it's positive z-axis. And the arrow, if I could draw it in 3 dimensions, would be coming right out of this board, would be the moment, the vector moment coming out like that. Okay? Now let me contrast that with the other case. What if I have point O here, okay, and I have point D, and instead of going that way, I'm going to act on it with a force that's pushing this way. What's going to happen? So this is the force, and this is the distance. So how is this thing going to rotate? Well, it's going to rotate like this. So from the right-hand rule, I again use my right hand. How is it going to rotate? I put my fingers in the direction of rotation. I'm going to rotate that way. My thumb points into the board. So that basically means that the vector that represents the moment is going to be pointing into the board. And because this guy is going to be rotating clockwise, okay, clockwise, then what that basically is going to mean is that the moment is negative, and this guy is also acting in the negative z axis. Basically what I'm saying is pretend that there's an xy plane here. So here's y, here's x. In this particular case, the moment's going to act into the board because z comes out of the board. Negative z is going to go into the board. That's going to be the direction of that moment. Whereas in this case, I curl my hands pointing out of the board, so the moment is going to be coming out. And it's all consistent. Whenever the moment points along the positive direction, positive z-axis, we say the moment's positive. When the moment axis, or when the moment points in the negative z direction, we say that the moment is negative. So basically the right-hand rule governs all that stuff, and if you've ever taken calculus or physics and you know the cross product of two vectors, which we're going to get to, you know that the cross product is basically using the right-hand rule also. So it's all self-consistent, it's just that the pictures that we're drawing now are in two dimensions to make it a little easier to understand. So let's get a little bit of practice with a little bit of this moment stuff. We're not going to do an actual problem yet, but let's just say, what would happen if we had multiple forces or multiple moments acting on an object? So we can say, this will be the topic of adding moments about the same axis. Because remember, moments always reference an axis. So for instance, what if I had some kind of nut or something, again, 6 sides, like this, and there's some point O, so that's going to end up being some axis of rotation. All right, so let's say attached to this, I have a piece of wood or a piece of steel or something that I've welded there, okay? And at the end of this guy, I'm acting with a force that's pointed like this, and I call this F1, okay? And then also down at the bottom, I attach another piece of steel or something much, much longer, okay? And I call this guy, or I say over here, that this guy has a force acting this direction, and I call this guy F2. And then just to make it, clear, I have another guy, some intermediate length over here, some piece of steel or something I weld onto there, and I say that there's a force going down like this, and I'm going to call this guy F sub 3. Now let me label a couple more things, because really, what's important here? The magnitude of the forces are important, but also the distance from the line of action to the moment arm is important. So this guy is acting on a line of action that's governed by that line. This guy is acting along a line of action governed by that guy, and this guy is acting along a line of action governed by this guy. So the lines of action are all there. The lines of action just means the force, the line that the force operates on. And also, what also is important is the moment arm, the distance from the line of action all the way up to the point of rotation. So this guy has a moment arm that we're going to call d sub 1. This guy has a moment arm called d sub 2, and this guy has a moment arm called d sub 3. And the moment arm is measured from the point of rotation to the line of action here, from the point of from the axis of rotation to the line of action here, and from the axis of rotation to the line of action there. So if there was only one force, how would you calculate the moment? You would say, okay, well, I didn't actually explicitly draw it here, but what I'm trying to imply by this is that this is 90 degrees here, this is 90 degrees here, and this is 90 degrees here, because remember, the moment is only dependent upon the perpendicular force that acts on the moment arm. And since all of these are already drawn to have forces perpendicular to the moment arm, then basically, if I were just looking at this one, the moment about this axis would be F1 times D1, right? And then if I cover everything else up, the moment here would be F2 times D2. And then here, if I just look at that one, the moment will be F3 times D3. Each one of these is going to form effectively a vector. The vector is either going to point out of the board or into the board, depending on which way this force tends to rotate this guy. And they're all going to be coming through the moment axis here. So since you have vectors that are stacked up on top of each other, those can be added. So essentially, just like if you have multiple forces acting on an object, and to get the resultant force, you add them all up, if you have multiple moments acting on an axis, you get the resultant moment by adding all of the moments up. It's not really rocket science. It's very, very, very consistent with everything we've been doing. So the way that you do this is you say the moment the resultant moment about the O axis. That's the way you write this. This tells me I'm adding vectors up to get a resultant about the O axis, okay, is going to be equal to, now the first guy, this one, is F1 times D1, okay? So F1 D1. Let's go and look at a few things. First of all, it only matters the perpendicular component of this force to the moment arm, so that's correct. The right-hand rule shows it going this way, so if it were representing as a vector, the moment would be coming out of the board, and since this force, forgetting about these, is tending to rotate this guy counterclockwise, we use a positive sign on that, okay? We use a positive sign. Now let's cover everything else up and look at what this one's doing. This guy is going to be F2 times D2, because again, he's also 90 degrees. However, this one is tending to rotate in the opposite direction of that one. So if I were to use the right-hand rule on this one, I would be curling in the direction of rotation. This one is going to cause a moment to go into the board, and consistent with that, as it's rotating clockwise, we already said clockwise rotations, we choose to write them as negative moments. So we put in a minus sign there. So we're adding up the moments. The first one creates a positive moment. The second one creates a negative moment, because when you think about it, this one is fighting against this one. He has to be negative in order to, have a contradiction to the first moment. The third one is F3D3, right? And which way is he trying to go? Well, I kind of use my fingers here, and I see, it's kind of hard, but if I grab and look at this way, my thumb is coming out of the board, and he is basically going counterclockwise as well, and so there's a plus sign. So basically, the two vectors that are tending to turn this guy in the same direction, which would be these two, one going this way, one going this way, these are trying to make him go counterclockwise, so we use positive moments for him, and this one is trying to go counter opposite of that guy, so we use negatives for him. So we were trying to find the resultant moment. We would find the moment due to the first force, the moment due to the second force, which is the opposite direction, the moment due to the third force. We'd add them all up, okay? And you're going to get one of two situations, okay? One of two situations is going to be the result of this. If the resultant moment about the axis ends up being positive, okay, then what does that mean? Well, we said positive moments rotate counterclockwise. That means that the resultant of all of this stuff is going to rotate counterclockwise, which is like this, okay? Or the other situation is the resultant, after we calculate it, is going to be negative, which means a clockwise rotation, which means like this. So it's putting into rigor what we've all done and kind of probably could do a thought experiment and think about. If I have 3 or 4 kids and we have long pipe wrenches attached around like a fire hydrant nut or something, and some of the kids are pulling and some of the kids are pushing, clearly the thing is going to rotate one direction or another, and it's basically going to depend upon who's strongest, okay, and who's overpowering the other guys. The way we keep track of it in mechanics is we define counterclockwise rotation to be positive, okay, and we define clockwise rotation to be negative. And then when we write the moments down, we look and we see what is each force trying to do, and we bookkeep it with positive or negative signs. The fact that these are multiplied is just the definition of the moment, and I'm warning you time and again that it's only the perpendicular component of the force along the line of action that actually does anything. We're going to get to a little more details in the next section about why that's the case, but for now, just know that the moment of a force always is around an axis, that it's the force, the perpendicular component of the force times the moment arm, which is the distance, that we have a sign convention for counterclockwise and clockwise to bookkeep the directions of the rotations, and in the back of your mind keeping track that the moment is also a vector quantity. So when we get to 3 dimensions and we're looking at arbitrary rotations, we're going to end up representing them as vectors and what will eventually be cross products later on. But for now, follow me on to the next section and we'll finally find out how to handle it if the force is not actually acting perpendicular to the moment arm. We'll figure out what to do. So follow me on to the next section. We'll talk about that right now.